What do we already know about refraction? We know that if you have two different media and light comes in at an angle, then it can bend when it enters the new medium. We also know that when we do our problem solving, we measure theta from the normal line, which is the dotted line perpendicular to the boundary or interface between the first and second media. So we use normal lines, we measure our thetas from the normal, and we also know that the amount of bending depends on the change in speed. In other words, objects refract because they change speed. And when I say objects, I really should say waves refract because they change speed. So let's consider this medium 1 and this is medium 2. And we know that there's this thing called the refractive index, which tells us, compared to the speed in a vacuum, how fast does it go in that medium? When dealing with light, we know that the speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. And we know that as this value gets slower and slower and slower, the refractive index will be higher. But this equation, while useful, doesn't actually refer to two different media. We could find the refractive index of medium 1 by using the speed of the waves in medium 1. We could find the refractive index of medium 2 by using the speed of waves in 2. But if we want to understand how much refraction, how much bending occurs while going from medium 1 to medium 2, we must use Snell's law. We learned this in the past, but we are going to learn it better now. Before we learn the more rigorous version of Snell's law, let's take this picture which shows a ray of light refracting, and let's add wavefronts to the picture. Remember what wavefronts show us. If we have a wave like this, and we have a bunch of waves all side by side, the wavefront connects neighboring crests. So we would draw a line right here going across. And there's another set of crests. What does the ray show us? Well, the ray shows us which way they're moving. And those two things are always at right angles to each other. Okay, wavefronts are perpendicular to the ray. So draw some perpendicular wavefronts. Let me start here, and then I go, okay, 90 degrees is like that. So here's my first one, and then there's another one, 90 degrees. And then, whoops, uh-oh. And then they have to be evenly spaced because the wavelength is constant. That's too close. Oh, well, let's just stop it there. Okay, now let's go into the new medium and let's draw wavefronts there too. All right, so that means I need to think about a right angle. So 90 degrees, is that a right angle? Pretty close. So then the first one is looking like that. The next one is gonna be, well, oh, you see this wavefront that we already started? Every wavefront will continue in the bottom medium. So let me just continue that one, and I wanna make sure it's parallel to the first wavefront. Are those parallel? Yeah, they look parallel, close enough. And then I continue this wavefront, and then this one. And then I keep on drawing more wavefronts equally spaced. Like that, all evenly spaced. And remember, these are all perpendicular lines. Nope. What do you notice about the wavelength? The wavelength is the distance between the two successive crests, and it decreased. Interesting. Lambda decreased. Do you remember, you may recall from a previous lesson, when the wave bends like this, did the speed increase or decrease? The speed decreased. And if you want to remember why, imagine a car traveling into the mud, and when the car slows down upon reaching the mud, this wheel, so here's the car, it's coming along this angle, and then this wheel slows, but this one keeps going fast, so the car kind of pivots, and then it travels at this different angle. The wave slows down when it bends in. Did the angle, theta, the angle from normal, did the angle increase or decrease? Theta also decreased. So it turns out when you move into a higher refractive index, everything else decreases. That's what the more rigorous version of Snell's law says. If we compare the refractive index of 1 to 2, everything else will be inversely proportional. Do you see that? N1 and its speed are on opposite sides of the fraction. Refractive index is, again, opposite the fraction bar from its wavelength in sine of theta. In other words, if you have a higher speed in medium 1, that would correspond to a lower value of n for medium 1. A higher lambda, again, lower n. A higher theta, lower n. So consider this scenario. Light passes from medium 1 to medium 2, and I have drawn in the wavefronts, not the ray like I normally draw. Which medium has a higher refractive index? Well, to figure this out, consider the wavelength, which goes straight between the crests. Medium 2 has a bigger wavelength, so what do you know about its value of n? N is less. Which medium has light traveling at a higher speed? Don't forget, refractive index is inversely proportional to everything. So if one has a bigger refractive index, it has a lower speed, a lower lambda, and a smaller theta. That means one has a smaller speed, a smaller lambda, and a smaller theta. Medium 2 has a bigger speed, a bigger lambda, and a bigger angle from the normal. This is another good chance to notice that these two things are directly proportional, and so are v and sine theta. So consider this question. In which medium does light travel faster? Okay, again, we can compare the different wavelengths. And we'll call this medium 1, this is 2. Medium 1 does have a bigger lambda. What does that mean for speed? Well, you may be inclined to say smaller speed, but that's not right, because everything is inversely proportional to the refractive index. So a bigger lambda means a smaller n, and a smaller n means a bigger speed as well. In other words, lambda and v are directly proportional to each other. Just for fun, let's go ahead and draw the ray. The ray has to be perpendicular to the wavefront. So then I think, okay, right angle, what's it look like? Like that, kind of? So we have this kind of bending that occurs. The light's coming in here, and then it whoosh, bends. The final idea to consider is when we show that ratio, n1 over n2, we can think of that as the refractive index of medium 1 relative to medium 2. In other words, it's the refractive index of medium 1 compared to or relative to medium 2. So this is a notation you may see, and it simply means this ratio. which is equal to speed 2 over speed 1, lambda 2 over lambda 1, and of course sine theta 2 over sine theta 1.